So Taylor polynomials. So let f be an infinitely differentiable function. Okay, what does that mean? Okay, it means that f, you could derive it and derive it first, second, third, fourth. You could derive it as many times as you want. Okay, forever. It will always be differentiable. Okay, so this could be translated graphically into a function that's very smooth. Okay, nothing pointy, no crazy behavior, like a nice smooth function. That's what it means. Okay, already differentiable is smooth, but infinitely differentiable is very, very smooth. Okay, so here we go. Taylor polynomial of f. So centered, so this is also important, centered at x equals a is, so here we go. So f of x is equal to this big sum, and goes from 0 to infinity of the nth derivative of f at a, because it's centered at a, divided by n factorial times x minus a power n. Okay, so it looks complicated, but you'll see that it's not. Okay, so what are we trying to do here?
So is it f power n?
It's here, this one.
Yeah.
This is the nth derivative. Yes, it's a little n here. It means the nth derivative. Okay. So what we're trying to do, okay, so if you look carefully, what do we have on the right? We have x minus a power n, and here that's a number, right? The function, if you derive it n times, and then you plug in a inside, a being a number, you plug in a inside, you get a number, divided by n factorial, that's also a number. So this is a number times x minus a power n. So it's basically a big polynomial. Okay, so it's called a Taylor polynomial. It's a big polynomial. So what you're trying to do here is to express a differentiable function as a polynomial, as an infinite polynomial. Okay, so a polynomial of degree infinite. Okay, at this point, let me expand this so that you could really visualize what we have here. Okay, so the 0th derivative, in other words, just f, we don't derive it. So f of a divided by n, which is 0 factorial, times x minus a power 0, plus, then n is 1. So the first f prime of a over 1 factorial times x minus a power 1, plus the second derivative of f evaluated at a over 2 factorial times x minus a power 2, and so on and so on. And you keep going like this. Okay, so this gives you an infinite polynomial. Okay, that is another way to express that function. Okay, So we could prove this. We could prove how he got to this, how Taylor got to this, but let's leave it for now. Okay, maybe if we have time, we'll do it. Okay. Okay, that's the idea. Just one thing that you have to know. I need to tell you that 0 factorial is what? Okay, so this is weird. Yeah, that's 1. Okay, 0 factorial is 1. Okay, why is that true? Forget it for now. We have to go into gamma functions to show this. And okay, let's leave it for now. Okay, so this is the Taylor polynomial. Any questions? Okay, let's do an example. Okay, so what we're going to do now is we're going to approximate a function by a polynomial. I'm going to stop it at, of course, I'm not going to continue till infinity. So I'm going to stop it at, let's say, 4 or 3, let's say a 3rd degree or 4th degree. And that would give me a polynomial that would approximate my function. Okay, any questions before I erase?
Sir, you said.
So here's an example. So let f of x is equal to, let's say, the square root of x. Okay. Find the, let's say, 4th degree Taylor polynomial of f. So around or centered, right? I want to do around a equal to 4. Okay, so I'm giving you a. A is 4. Okay, that's the first question. Second question, use that polynomial to approximate let's say the square root of 4.05. Okay, so 4th degree. That means that I'm going to find the first 5 terms, basically, okay, of the polynomial. It can go on forever, but I'm going to stop at when I get to the power 4. Okay, so let me write this, what I have. F of x is approximately equal to, okay, so the first will be f of 4 over 0 factorial times x minus 4 power 0 plus f prime of 4 over 1 factorial times x minus 4 power 1, right? Plus f prime prime of 4 over 2 factorial times x minus 4 power 2 plus f prime 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 of 4 over 3 factorial times x minus 4 power 3 and plus f the 4th derivative at 4 over 4 factorial x minus 4 power 4. And I'm stopping here because they tell me 4th degree. Any questions with this? All good? So the 0, the 1, the 2, the 3, the 4. I'm stopping at 4, although I could go on to 10 million if I want. Okay, so I'm going to definitely, my function is f of x equals root x. I'm going to need the first derivative, second, third, fourth derivatives. So let's do them here. Okay. So f of x is root x. Oops. F prime of x. So the derivative of root x is 1 over 2 root x, or 1 over 2 root x. 2. So turn this off. Okay. Second derivative. So the derivative of this. So I'm assuming you know how to do this. So I'm going to go right away. So I get negative 3 over 4 x to the, no, sorry, negative 1 over 4, sorry. X is 3 over 2. Third derivative is 3 over 8 x to the 5 over 2. And the fourth derivative is negative 15 over 16 x to the 7 over 2. Can you still see? Yeah. Who's got questions on this? Okay, so this is x power a half. Derives, you get 1/2 x is negative a half. X is negative 2 over 2. Derives, you get 3 over 2 times x is negative 5 over 2, and so on. Okay, so you derive. Okay, so what do I need? I need all these evaluated at 4. So let's go. F of 4 equals f prime of 4 equals f prime prime of 4 equals f prime 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 of 4 equals, and f 4 prime of 4 equals. Okay, so f of 4, so square root of 4 is 2. That's easy. F prime of 4, plug in 4 here, you get a quarter. Easy. F prime prime of 4, plug in 4 here, you get, I think, negative 1 over 32. Plug in 4 here. So 32 times 8 is 256. So 3 over 256. And negative 15 over, so what is that? 112048, I think, unless I'm wrong. X power 7, 2 power 7 is, so 4 and 7 is 11, well, that's 2048.
Sir, could you
Yep.
explain the mental math that went into solving 2048?
Here on the bottom, this one.
Yes.
So what I did, okay, maybe I'm wrong. I don't know, maybe I made a mistake.
No,
So
you're right. I just checked, but I'm interested to see how you're able to do that.
Oh, okay, because what I did, it's 16 times 4 power, that's what I did in my head, okay? 4 power 7 over 2. And so 16 is 2 power 4, okay? And 4 power 7 over 2 is like 2 power 7. So that's like 2 power 11, right? That's what it is, 2 power 11. And I know that 2 power 10 is, I know that this is 1024, this I know. And 2 times 1024 is 20. That's what I did. Okay?
Okay.
Okay. So, done. We now need just, the only thing we need now is to replace all these derivatives, all these values inside here. Okay, so it's just really arithmetic. It's nothing really complicated here. Okay, so let's go. So I think I'm going to need space here. So basically the square root of x, okay, f of x, which is square root of x, is approximately equal to, so here we go, f of 4, which is 2, over 1 times 1, so just 2. My first term is 2, plus f prime of 4 is a quarter, over 1 factorial, which is 1, times x minus 4, power 1. Then f prime prime is negative 1 over 32. So minus 1 over 32 times 2 factorial, which is 2, times x minus 4 squared. Are you guys with me? Am I going too fast for anyone?
You're going a little too fast.
Okay. Oh, I'm going to wait 2 seconds.
Are you just multiplying everything you found earlier with x minus 4 to the power of n? Is that what you're doing?
I'm just, okay, so just to be sure, is everybody okay with the derivatives here? Anybody ask question with these derivatives before I continue? I could go back here and re-explain if you need. Okay, no one sure? Okay, so what I'm doing is this is my Taylor polynomial on top. I'm just replacing the values I found here on the left into f of 4, f prime of 4, f prime prime of 4, this one, and this one. That's what I'm doing. Okay, so f of 4, I know it's 2. F prime of 4 is a quarter. Here it is. And so on. Negative 1 over 32, I replace here. Negative 1 over 32 over 2 factorial. And the x minus 4 squared is still here. You guys still lost?
How does the 2 factorial become 2?
Because 2 factorial is 1 times 2. Right? That's 2 factorial is. And 3 factorial here will be 6. 1 times 2 times 3. That's 6. And this will be 24. Good?
Yes.
Okay. So I'm going to keep going. Okay. If it's too fast, just stop me. Okay. Don't hesitate to stop me.
Sir,
Yeah.
why does, I know minus 1 over 32, but why is it not minus 1 over 32 over 2? Why is it
This
times?
isn't, okay. 1 over 32 over 2. That's what you're saying?
Yeah.
Okay. So this is like same thing as 1 over 32 times 2 over times 1 over 2. And that is 1 over 32 times 2.
Okay. Thank you.
Good?
Yeah.
Okay. There's no question that you can't ask. Okay. Ask everything. Okay. I'm assuming I do it fast because I'm assuming that you've done enough that you know this. Okay. But if not, fine. Now you know. Any other questions? Okay. So I'm going to continue. And again, if you hesitate, you stop me. So plus f prime prime prime, which is 3 over 256, times 3 factorial, which is 6, times x minus 4 cubed. And the last one, minus 15, so I have space, over 2048 times 24, times x minus 4 power 4. It hits. And that's my polynomial. Okay, it's a polynomial, a 4th degree polynomial. I could expand, I could do whatever I want, but I'm going just to simplify the coefficients at least so that I could see a bit clearer. So the square root of x is approximately equal to 2 plus 1/4 times x minus 4 minus 1 over 64 times x minus 4 squared. And what is that here? Plus 1 over, this is 512. If I reduce the fraction, and minus, now this one's a bit more annoying. So 5 over x minus 4 power 4. So can you tell me what 8 times 2048 is? Somebody tell me.
16,384.
There you go. Okay. And that's my polynomial. This, I just answered question 1, my first one. Find the fourth degree Taylor polynomial around a equals 4. Here it is.
Sir,
Are there any questions? Yeah.
when we say 1 factorial, that means that it's just 1, but like 2, it's 2 times 1, and then
Yeah.
3. Okay.
It's 3 times 2 times 1. Yeah. Okay. The second part, the second question is to use this polynomial to approximate the square root of 4.05. So let's do 4.05. Okay. So you know what? I'm going to do 2 of them, and even the square root of 5. Let's approximate the square root of 5 as well. Okay. So the square root of 4.05 is approximately equal to what? So I just need to plug in 4.05 in here. So I get 2 plus a quarter times, so 4.05 minus 4 is 0.05. Then minus 1 over 64 times 0.05 power 2 plus 1 over 512.05 power 3 minus 5 over 16,384.05 to the power of 4. Okay, let's calculate this for fun. See what we get. Okay, I'll do it also. Okay, I get 2.012461118. This is what I get. Can anybody confirm that?
Yeah, I got the same thing.
Perfect. And let now take your calculator and do square root of 4.05, the exact value, without using the polynomial, and you'll see that you're going to get almost the same thing.
Sir,
Yeah.
did you just replace all the x's in the polynomial with a number we're trying to
4.05.
approximate? Yeah. Okay.
Exactly. Okay, so that's very, very close to the real value of the square root of 4.05. Okay, so before they had calculators, that's how they would evaluate square roots. They would estimate square roots like this. Okay, because in theory you don't need a calculator to do this. Okay, you could do it. It's a long division to do, but you could do it. It takes time, but you could do it and bypass the calculator. Okay, let's approximate the square root of 5 using this now. So it's going to be less precise because we're further away from 4. Okay, so 2 plus 1/4, oh, this is all 1, minus 1 over 64 times 1 squared, plus 1 over 512, 1 cubed, minus 5 over 384, sorry. Times 1 to the power of 4, and so we get, what do I get here? 5 divided by 16,384.
Sir, isn't it 15?
Here?
Yeah.
Here? No.
But why did it change to 15?
1 second. I'm going to show you right now. Okay, I get 2.236 0222949. Okay, let me see. Okay. Why? So your question, how did this become from a 15 to a 5?
Yes.
Okay, because I simplified, I divided the top and the bottom by 3.
Oh, okay.
Okay. That's why I just did 2048 times 8, not times 24 to get this. Okay, so here's an approximation for the square root of 5. I get 2.2360. So what's the real value of square root of 5? Let's find the real value to compare. What can we do? So 5 square roots. Oh, not bad. 2.236067977. Okay, so I'm good. The first 1, 2, 3, maybe 4. So I'm good for the first 4 digits. Okay, so the closer you are to what you're centered at, the more precise you're going to be fast. I could be more precise, but I need to continue in my polynomial. I need to go to a degree, maybe 10, to get more precision.
So
That's it. Yeah.
how did you know you have to take 4 derivatives?
Oh, I asked you. I didn't know that. The question comes like this: 4. Because this is the, oh, somebody's in the waiting room. This is the level of precision that I'm looking for. Okay, if I wanted more precision, I would have said 10th degree. Okay, so on the exam, on the test, on the exam actually, I'm not going to go more than 4 guaranteed because it takes time. You see that it took time. Okay, and it's very easy to make a calculation mistake, and that's not what I'm testing. I don't want you lose points for calculation mistakes, but I just want you to understand the idea. So the MacLaurin series. Okay, so the MacLaurin series of function f is its Taylor polynomial. It's the same thing as what we just did. But it's centered at 0. That's it. Okay, the MacLaurin series is exactly the same as the Taylor polynomial, same thing, except that it's centered at 0. Okay, so let me write it like this: f of x is equal to the sum n equals 0 to infinity. So it will be the nth derivative, just like before. Now, instead of a here, I have centered at 0 over n factorial, just like before. And here, instead of x minus a, I'll just have x minus 0, so x power n. This is the MacLaurin series of function f. This is much easier to evaluate, right? To express. The only thing is that we're going to have to find the general term now of the MacLaurin series. Okay, so let me give you an example on finding the MacLaurin series of sine x. Okay, so we're going to do the classic ones, the most important ones, which are sine x, cos x, e to the x, and ln of x plus 1. Okay, so we'll do these ones. So example, find the MacLaurin series of, so the first one, f of x is equal to sine of x. Okay, so I'm going to have to note that I'm not telling you the 4th degree or 5th degree. I'm telling you just find a series. So I want all the terms. Okay, so you have to express as a series. You can have the sigma notation here. Okay, so I have to find the pattern. So let me go here. F of x is sine x. So I'm going to need f prime. F prime is cos. F prime prime, the derivative of cos, negative sine. F prime 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 is negative cos. And then F4 prime, well, I'm back to sine. And again, I keep going. Okay, so it resets. Okay, the next one will be cos, negative sine, negative cos, sine. Cos, negative sine, negative cos, sine, and so on forever. You with me? Okay, so dot, dot, dot. And of course, I need to evaluate them at 0 this time. Before it was at 4, at A, now it's at 0. So let's do. F of 0, sine of 0 is 0. F prime of 0, so cos of 0 is 1. F prime prime of 0, which is negative sine of 0 is 0. And F prime 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 of 0, which is negative cos of 0, which is negative 1. And then 4th derivative, sine of 0 back to 0. Okay, so it will be 0, 1, 0, minus 1, 0, 1, 0, minus 1, and so on. Are there any questions before I continue? I'm going to write down here. So sine of x is equal to, so f of 0 over 0 factorial. So f of 0 over 0 factorial plus f prime of 0 over 1 factorial times x plus f prime prime of 0 over 2 factorial times x2 dot dot dot. I'm just expanding this sum. You with me?
Yeah.
Okay, so equals. So let's go. F of 0 is 0. So my first term is 0. Second term, f prime, so it's 1. So plus 1 over 1 factorial times x. Then plus f prime prime of 0, 0 over 2 factorial times x2. Minus 1 over 3 factorial x3 plus 0 times over 4 factorial times x4. And then the next one will be plus 1 over 5 factorial times x5, and so on and so on. Okay, I'll continue up here.
Sir,
Yeah.
how many how many terms are there gonna do?
So you're going to continue until you recognize a pattern.
Okay.
Okay. So I think I recognize the pattern here because I get, so these zeros, they cancel. So all the even terms will cancel, it seems. So I have x over 1 factorial minus x cubed over 3 factorial, then plus x5 over 5 factorial, then minus x7 over 7 factorial, plus and so on.
Sir,
Yeah.
is the answer to this 0?
What the answer is? What, 0?
Yeah,
Why would it be 0?
because if the pattern of like if you look at the first 4, so from f of 0 to f of 3, it adds up to like 0 plus 1 plus 0 plus minus 1 equals 0. And since that pattern is going to be repeating always, because whenever you derive it.
I didn't understand the first thing you said. What do you mean 0 plus minus 1? What? What did you say?
Oh, when you add up the sum, like when you take the sum of the first 4, you get 0.
You mean this here?
Yeah.
No, but there's x here times x and divided by factorials. That's not 1 minus 1. It's 1 times x over 1 factorial minus 1 times x3 over 3 factorial plus. These are only the little coefficients here. This doesn't cancel.
But the like when you make the sums, right? You add up the what it is at f of 1, then you go on.
No, I'm not adding these. Look, these here, what I found here, wait a second, my finger. What I found here, okay, is just this part. These terms.
Okay.
So this I have to divide by n factorial and times by x power n.
I see.
Okay, it's not.
Okay.
You're right. If there wasn't the n factorial and there wasn't the x power n, true, it would just be 0 plus 1 plus 0 minus 1 plus 0. Okay. And yeah. I'm not sure if this would cancel, by the way. Okay, it's an infinite series that alternates. It's an alternating series that does not necessarily converge. It doesn't converge, actually. Okay, so you guys okay with this?
Sir, I don't understand where
yeah, tell me.
How you went from the one, like the last 2 steps.
The last 2 steps. So how did I find this one here?
No, how you went from this to the other one.
Oh, from here to here?
Yeah.
Well, I just cleaned it up. I took out the zeros. Okay, so this out, 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 right? Because 0 times something. That's all I did.
Yeah, okay.
It's good?
Yeah.
Okay, so now I need to find a general term. Okay, so the sine of x is equal to, so let's express this as an infinite sum. 0 to infinity, so here we go. X to the power of only the odds. 1, 3, 5, 7. How do I express an odd number?
I'm not sure. Is it like n plus 1?
So n plus 1 won't necessarily be odd.
2n plus 1.
Oh, 2n plus 1. 2n plus 1 is good. Okay, so x power 2n plus 1. So let's verify. If n is 0, 2 times 0 plus 1 is 1. Perfect. If n is 1, 2 times 1 plus 1 is 3. Good. If n is 2, 2 times 2 plus 1 is 5. Good, and so on and so on. So this generates all the odd numbers: 1, 3, 5, 7, 9, 11, and so on. Okay. The bottom, what do I have here? 1, 3, 5, 7 factorial. What do I write here?
Could we write the same thing? So 2n plus 1, factorial.
Perfect. So 2n plus 1, that number factorial. Exactly. Good. There's only one thing that we didn't take into account. What is it?
The sign.
Very good. The fact that it alternates plus, minus, plus, minus. So what do I need to put here?
Minus 1 to the power n.
Very nice. Minus 1 to the power of n. And that's your MacLaurin series for the sine function. Okay, so if you want to express sine function as an infinite polynomial, that's what you have to use. Here it is, expanded. Here is the general sigma notation form. Okay, so if you remember, okay, we said that the sine function was the graph of the sine function was like this. Right, this is the graph of the sine function. What type of function is it? You remember? We did this together. This is called then what type of function? It's symmetrical with respect to the origin. Anybody? What?
An even function.
No, it's an odd function.
Oh, sorry.
Okay, it's an odd function because it's symmetrical with respect to the origin. Okay, so, and as you see, if you do the expansion, you get only odd exponents. That's why it's called an odd function. Okay. Okay, so number 2, f of x is equal to the cosine of x. So let's go. F of x is cos x, f prime of x is negative sine x, f prime prime is negative cos x, f prime 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 is sine x, and f4 prime, I'm back to the original cos x. Okay, and so on. Let's find evaluate them at 0. F of 0, f prime of 0. Okay. Okay, so if I plug in 0 here, I get 1, 0, negative 1, 0, 1. Again, so 1, 0, minus 1, 0, 1, 0, minus 1, 0, and so on. So cos of x. So again, f of 0 over 0 factorial plus f prime of 0 over 1 factorial x plus f prime prime of 0 over 2 factorial x2 plus f prime 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 of 0 over 3 factorial x cubed, and so on. So I get what? 1 over 1, so that's 1. Then this is 0. Then minus 1 over 2 factorial x2. Plus this is 0, because f prime 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 is 0. Then plus the fourth one, so 1 over 4 factorial x4, and so on and so on. Okay, so I just have the even one. So 1 minus x2 over 2 factorial plus x4 over 4 factorial. So obviously, the next one will be minus x6 over 6 factorial plus x8 over 8 factorial, and so on and so on. Let's find the general term, the general MacLaurin series. Sum n equals 0 to infinity. So can you tell me
Not
X
sure
to
if
the
it's
power of
correct.
x to the power of what?
Would n plus n work?
N plus n, so 2n.
2n, yeah.
Yeah, 2n over 2n factorial. Good.
Times -1 to the power of n.
Very nice. Times -1 to the power of n. And that's my MacLaurin series for the cosine function. And the cosine function, if you remember, was the graph was like this, which is symmetrical with respect to the y-axis, which is an even function. Okay, and as you see, the exponents are all even. It's an even polynomial. That's why it's an even function.